My research focuses on the earthquake, especially for the recurrence pattern and the seismic signals and the seismic events. And so today I will present my recent research on the earthquake, especially for the Parkfield tremors. And okay, let's see the title. The title is it can be divided into two parts. The first part is the period multiplying cycles at the transition between steep and steeper sliding. And then we can discuss the implication for the Parkfield period doubling tremors. First, I will introduce the background of my research and present the experimental preparation and direct shear experiments on granite and polycarbonate fractures. And then we can discuss the results and make some conclusions. Finally, I will present my future work. Okay, here shows the seismic map and near the Parkfield on the San Andreas Fault. We can see that the red star is the 2004 Parkfield earthquake. It's a big earthquake, and we can also observe a sequence of low frequency Parkfield tremors, and we can see that here shows the room of the sequence of low frequency tremors, and before and after the Parkfield big earthquake, and the sequence and the tremors change a lot. Before the earthquake, we can see that the Parkfield tremors always oscillate into two events, and the recurrence time always change from the 3 days and 6 days. But after the earthquake, we can see that the recurrence time change a lot, and after about 2 years, it returned to the original recurrence pattern. So here comes my research question. So, we can cause it as because the tremors always alternate between 3 and 6 days. We can call this formula is the period two cycles. So the question is the mechanics of period two cycles remains poorly understood, and especially how the coupling between fault slip and the seismic emissions of Parkfield tremors. And okay, previous study already shows that the fault slip behavior is controlled by two factors. The first factor is the stiffness ratio, K, and the second factor is RB. And okay, let's see the first factor. The stiffness ratio is the ratio between the system stiffness and the critical rheological stiffness. Normally, the system stiffness is a constant value, the K, but the Kc it consists of the frictional properties and the effective normal stress, so it can be changed. Once the stiffness ratio K is smaller than 1, we can observe the faster stick slip. That means the regular earthquake and the bigger earthquake. When the K is approaching to 1, we can observe the slow slip, such like the period 2 cycles and the period 2 doubling. And when K is bigger than 1, we can observe the stable sliding. It means the fault creep. There's no seismic events. And because the Kc is very important, and it can be and it's related to the critical steeper distance, the frictional parameters, and the effective normal stress. So we conduct the step velocity experiments to obtain the frictional parameters like the DC, A, and B. We can see that the one we just changed the load point velocity from V0 to V1. We can find that the frictional coefficient changed, and then we can measure the A, B, and DC. So, so we can determine the critical rheological stiffness. And the second factor is the RB. RB is the ratio of static to dynamic stress drop. and it can control the emergency of period multiplying cycles. And so, and in our experiments, we will change the normal stress sigma n to produce the period 2 cycles. And then I will use two different fractures, granite and polycarbonate, to change the frictional parameters A and B. So that's the background. And here shows the experimental setup. Okay, here the big one. And we can see the schematic diagram of the direct-shear operators. And the direct-shear operators consist of two plates, the fixed plates and the drawing plate. And they are pressed together by the normal load. So, and the interface between them is used to simulate the fracture, and then we apply the shear load to drive the shear drawing plate to slide along the fracture. And we also use the acoustic emission sensors to monitor the seismic signals, and also use the LVDT to measure the displacement. And here, okay, here left one is my sample granite and polycarbonate. We can see that the mechanical properties of them are totally different, especially for the Poisson's ratio, density, and the shear modulus, and the frictional parameters A, B, and DC. And of course, I will use a 3D scanner to scan the fracture surface, and especially compare the difference of the fracture surface before and after my experiments. And so okay, here shows the direct-shear experiments on polycarbonate and the granite fractures. And the left one is the results of polycarbonate, and the right one is the granite results. And we can see the red line, it means the normal stress. The black line, it means the shear stress. The load point velocity in my experiments is constant, 180 micrometers per second. But the normal stress will decrease and unloading steps from 2 to 0.6 megapascal, and the interval of normal stress is about 0.2 megapascal. And we can see that the fracture slip behaviors is different and different normal stress. And I divided them into 3 stages: stick slip, period multiplying, and stable sliding. And so what's the difference of them? Okay, in the stick slip, we can see that there's big sharp, there's sharp straight drop. It means the seismic event. We can see that the recurrence time and the stress drop is almost constant. The recurrence time means the time between the 2 seismic events, and the stress drop is the difference of the stress. So we can see that the recurrence time and the stress drop is almost constant in the stick slip. But for the period multiplying cycles, we can see that the recurrence time and the stress drop show a great oscillation. And based on so we can calculate the stiffness ratio based on the normal stress. We can see that when the k is smaller than 1, we can observe the stick slip, and when the k is approaching to 1, we can observe the simple transition, like the period multiplying cycles. And finally, when the k is larger than 1, we can observe the stable sliding. So both the fractures exhibit the stick slip, period multiplying cycles, and the stable sliding, but we can also observe the difference of the stiffness ratio k. It can be attributed to the different Poisson ratio, frictional properties, and the physical dimension of the whole samples. You can see that it's a bit different, especially for the pure multiplying cycles. Okay, here we compare the source characteristics of the snip events during the stick snip and the period multiplying cycles for polycarbonate and granite fractures, such like the stress drop and the acoustic emission energy, duration, count, and the snip deficit. So we can see that there are difference of the source characteristics between the stick snip and the period multiplying cycles. In the stick snip, we can see that the shear stretch drop, A duration, A energy, A count, can keep roughly constant, and the snip deficit is almost the same. But for the pure multiplying cycles, we can see that there is the greater oscillation. The source characteristics always oscillate between a big one and a small one. And of course, when we compare focus on the pure multiplying cycles, we can see that there are difference between the polycarbonate and the granite. The pure two cycles on polycarbonate fractures are much regular than the granite. We can see that the one for the granite, we can see that the shear drop is show a great oscillation and show great variability. But for the polycarbonate, we can see that they are very regular, a big one and a small one. So the difference of the source characteristics can be attributed to the controlling factors K and RB. And so I calculate the K and RB. We can see that for the granite, the controlling factors are more unstable than the polycarbonate. So the sequence will randomly snip from period 2 to period 3 and to deterministic chaos. So in generally, because the K and RB on granite is much unstable than the polycarbonate. So that's why the period 2 cycles on polycarbonate is very stable. So, but what contributed to the unstable snip behavior on granite? So we use the 3D scanner to obtain the fracture surface before and after the experiments. We can see that before the experiments, the surface roughness is almost the same, but after experiments, we can see that the granite surface, the roughness is much larger than the polycarbonate, and so so the granite fracture experienced more aberration with a shear of thickness of 29 micrometer, almost trace the 11 micrometer for the polycarbonate fracture. And the mean square roughness also suggests a more severe change in surface topography on the granite fracture. So the shear of particles on the granite fracture accumulate at the gouge layer with distinct frictional property, and we can therefore attribute the variability of snip sequence on granite fracture to the change of shear layer. And finally, I compared our experimental results with the Parkfield tremors. We only focus on, because the Parkfield tremors is the pure 2 cycles, so we can only focus on the pure multiplying cycles and the cycles. So we can see that the seismic events in the period multiplying cycles can be divided by the equal interval line. And but many events fall within the doubling and halving interval line. And we can also see that there is the positive correlation between the velocity amplitude and acoustic emission energy and recurrence time. There is the positive correlation. And it means that the fracture can accumulate more strain energy after long seismic period. So, and there is the successful comparison between the experiments and the Parkfield tremors, especially for the recurrence pattern asynchronous and velocity amplitude. And so our experiments, experimental results can provide provide a direct demonstration about the to explain the variability of recurrence time at Parkfield. Okay, we can see that the Parkfield tremors show greater oscillation and the variability. So the accumulation of gouge and associated change of frictional parameters over time may explain the variability of recurrence time at Parkfield and the high sensitivity of tremor cycle to outside perturbations. So of course, our experiments has its limitations, especially for the vector fault geometry and the source mechanism. So here we can get some conclusion. The first one is the pure multiply cycles can appear as the transition from stick snip to stable sliding with a stiffness ratio approaching to 1. And secondly, the difference of period multiplying cycles for the polycarbonate and the granite fixtures, probably due to the different the elastic properties, sample dimensions, and the ratio of frictional parameters A and B. And the third, and the polycarbonate fixture is sheared more uniformly and exhibits steady period 2 sequence. In contrast, the granite fixture developed a thicker gouge layer with varying frictional properties, leading to the irregular period n cycles. And of course, the experimental results provided direct experimental supports for mechanical link between the energy, velocity, amplitude, and shear stress drop and the recurrence time, and time of the step events during the period 2 cycles. And the evolution of the period 2 cycles may be related to the normal stress and the fracture heterogeneity. So here's the conclusion. And I also will continue my future work. The first one is the effective of load point velocity on the recurrence ratio of fast to slow ruptures. We can see that the transition between stick snip and stable sliding, but with the load point velocity change, we can see that under a very high load point velocity, the recurrence time is almost the same, but under very slow load point velocity, the recurrence time show greater oscillation. And the second one, I will study the effect of uncertified treatment on the stable transition between stick snip and stable sliding. We use the HCl to treat the granite surface after 1 to 45 days. Here shows the SEM results of granite surface topographies, and we can see that after a long acidified treatment, we can see that the microstructure on the granite surface is very clear. So it can be change the frictional properties of the granite surface, and then it can affect the seismic cycles. And finally, also continue my research on the machine learning of fractures behavior. The first one is the laboratory seismic cycles, and the second one is the microseismicity at the gold mine in South Africa. So we use the machine learning to get the very performance of the simulation. So that's my future work. Okay, that's my today's presentation. Thank you.